All right. Um, Hi, everybody. Thanks for coming. This is a talk about Shapeless. My name is Edoardo Vacchi. I work for UniCredit Research and Development Department. And these are my handle. You can find me on Twitter, on GitHub. And the full text of this talk you will find on this blog, Arenduia, GitHub.io, where we write with some friends, colleagues. And you'll find the full text of this talk. So if you miss some details, don't worry. And of course, you're free to pose any question that you have in your mind, to stop me for us more clarification. So during my everyday job experience, I came across a problem that I had to solve, and in the end, I had to use. I decided to have a look at Shapeless. The problem had to do with data flow programming. So, does anybody here knows about what data flow programming is? 2 persons, all right. And does anybody know here what reactive programming is? All right. It's the same thing. So, it's just the data flow programming is the literature, the name from the literature, but it's exactly the same thing. And it's basically it has to do with dealing with pipelines. So you know shell pipelines, like, like you pipe the output of a command inside the input of another command, you pipe it to the other input of another command, so on and so forth. So these are data pipelines. They're fancy. They're fancy stuff today. They're huge with big data processing. We do for big data processing of big data pipelines. How would you define a pipeline using Scala? You might define a case class like this, a case class which takes 2 type parameters, t and r, t for the input, r for the return type, and then it will take a function from t to r. Then as the data flows through the node, that's the name, data flow programming. As the data flows through the node, the function will be applied to each data point, and then the result of the application will be put on the output of this data processing node, right? So that's what you will do. You will call the function f on t, and then write it on the output. This is pretty simple, pretty nice. But what if we have to deal with graphs? So it's a little bit more complicated, right? Because now each node takes more than one input. So it takes more than one input, so it's more complicated to write it using Scala, for instance. We will know how to do this with a fixed number of inputs. So with functions of a fixed arity. What's arity of a function? The arity of a function is the number of parameters it takes, right? So a binary function is a function with a 2 arity because it takes 2 parameters, right? So how would you implement this? I'm not sure you can actually read this. Anyway, you will write a node which takes a t1 type, a t2 type, and r for the return type. And then the function will be defined with a pair which is made from t1, t2, and returns r, right? Then you will read first from one input, read from another input, and then you could apply the function to the tuple of these 2 inputs. In fact, in Scala, this is pure Scala, no magic here, no libraries. If you write this f.tupled, you get the function, the unary function that takes a pair. So if you have a function that takes 2 arguments, f.tupled is the unary function that takes the pair. Clear? Is it clear? Pretty simple, right? And so we could construct the pair with the 2 inputs and then apply it to this function that we get from f.tupled. That's pretty easy, right? It's very simple to understand how this could be generalized, right? So you could write it for 3 arguments, for 4 arguments, and so on and so forth, up to 22, right? Because that's the limit. Actually, this is going to be solved in .t, or I think it is already solved in .t. It's been announced during Scala Days, New York City 2016. So they're going to use H-lists. We'll see this in a moment. But anyway, right now, if we want to use Scala, that's a problem. So we want to define a node that takes an arbitrary number of parameters, so a node that takes a function with arbitrary arity. And we have two problems, and we want them to apply this to an arbitrary number of parameters that matches in size and in types with the function that we're giving. So the problem is now, how do you construct a k-tuple for any k, so any number of parameters, and what will the type signature for node will then be? The problem is that we have all these specific different types for each number of parameters that we have. So one way to solve the problem would be to do code generation, right? We could define node 2, node 3, node 4, and so on and so forth, and then take a function of different arity for each of these nodes implementation. But then this will be complicated. When you generate code, generating code is error prone. I mean, it's not something that scares us. We're pretty accustomed to generating code with Java, you know, because the type system of Java is much less powerful than Scala's. But with Scala, we would like to be able to use the type system to help us here. We have macros which can help us, but still code generating is not the best way to do stuff because it's more error prone. How do you test that? Would you then generate the tests to test the generated code? Yeah, it starts to become pretty complicated soon. So we could use reflection, right? You can reflect over your code, instantiate stuff at runtime, and then blow up at runtime spectacularly. So that's not really the best way to do this as well. So maybe you might have heard that Shapeless could be helpful here. So maybe people here might have wondered why the name Shapeless and why the name of this talk is Be Like Water. There's a talk by a guy called Sam Halliday, which presented a talk, a very nice talk that I suggest to you, entitled Shapeless for Mortals, from which I took some inspiration. And he's one of the guys who developed Enzyme. And he quoted this citation, right? Don't get set into one form. Adapt it and build your own and let it grow. Be like water. Empty your mind, be formless, shapeless, like water. You put water in a cup, it becomes the cup. You put water into a bottle, it becomes the bottle. You put it in a teapot, it becomes the teapot. But water can flow or it can crash. Be water, my friend. So this is from Bruce Lee, if you don't know. Yeah, it's true. Actually, when I published the blog post on the Arenduia, Miles Sabin, who's the author for Shapeless, actually replied to the tweet and said, well, it doesn't really come from that quote, but it works as a metaphor, so. Okay, so Shapeless. The problem with Shapeless is a little bit with the documentation. There's not much of it. It is sparse, and it is not really oriented to beginners. So when I started to think to this problem, the problem of nodes and data flow programming, I started to think, well, I have to abstract over arity, right? So maybe I could look up with Google, Shapeless, abstract over arity, bam. There's the Shapeless wiki. Wow. So facilities for abstracting over arity, that's it. We could just copy and paste and be done with it, you know, call it a day, go home. But let's have a look at it a little bit closer because I'm not used to just copy and pasting stuff. So, all right, there's some type parameters, there's some implicit things, there's I don't know. And then there's some, this is going to be applied to some parameters, and then there's a, I don't know. Okay, this is a little bit confusing, right? So maybe the description on the Shapeless wiki for this code snippet is gonna enlighten us. All right. So it says conversions between tuples and h-lists and between ordinary Scala function of arbitrary arity and functions which take a single corresponding h-list argument allow higher order functions to abstract over the arity of the functions and values that are passed. What? All right. said H-list a bunch of times, so it must be important, right? Okay. What's an H-list? An H-list, I hope you're able to read what's written here. An H-list, it's the name for heterogeneous list. It's a list that can contain heterogeneous types, different types. That's fine, but lists can contain heterogeneous type. I can put an integer and a string inside the same list, right? That's what's above. But then the list will be typed with, what will be the type of it? Any. So if I try to get back an element from that list, I will get any. That's not what I want. I would like to be able to know what the type of that value is. And so here comes the H-list. With H-list, I basically can construct a thing that maintains the types of the things that I put inside. The next thing is H-list also support all of the stuff we're accustomed to with lists. So we can pattern match, we can deconstruct, and also we can map, fold. So that's really powerful, and that's implemented in Shapeless. So in this talk, I'm not going to delve into the details of how H-lists are implemented, because it's not really important. Actually, they're quite simple. There are a lot of talks, one of which my colleague gave last year at Scala-italy 2015, which I suggest. So it's not important right here, right now, because H-lists are actually tuples. In fact, the objective of today is not to really understand how Shapeless is implemented, which is the problem with many of the blog posts you find on the internet. They're trying to make you understand how Shapeless works, but by telling you how it's implemented. But we don't really want to know this right now. We would like actually to know if it's useful for what we want to solve, so how we can use it. So let's see how it can be put to good use, right? So H-lists can be seen as tuples. You can construct tuples, then you can construct H-list. You can deconstruct tuples, you can deconstruct lists. You can pattern match H-lists, but only for all of their arguments, right? For a tuple, you can only, if you have a tuple of three elements, you have to pattern match all of the elements and possibly discard those that you're not interested in. But H-lists behave like lists. So you can abstract over the arity of that particular kind of tuple, which is called an H-list. You can pattern match of the first element regardless if it's a two-tuple, a three-tuple, a four-tuple, a don't-know tuple. You can pattern match over the first two elements. So if the size is at least 2, and then you can pattern match when the size is exactly 2, when it's basically a pair. So you can basically abstract over arity because you can pattern match over the head and the tail, like for lists, right? And also, you can pass and convert from H-list to tuples and case classes. So you can construct that H-list, which has an integer, a string, and a double, and then use use the method called tupled to convert it into an equivalent tuple, a string and an int. Oh, I'm missing a double here. Compile error. Well, don't worry. All right, no problem. Then we have product elements to convert a tuple into an H-list. And then we can apply product elements to convert a case class into another H-list. So all these things look a lot related, right? Because I can convert between all of them. So probably they have something in common. Well, first of all, right. So we've seen that we can convert between these things. These are methods that are provided through Shapeless. How do they work? They work because under the hood, they're using an object called the generic. You know, the thing that I was saying, the documentation is very sparse. Also, the naming conventions are not very, talking. Anyway, the generic object is the thing that lets you convert between a case class and an H list, or possibly a tuple and an H list. It has these two methods, to and from. And you can convert to an H list and from an H list into another type, a tuple, for instance, or a case class. Now, we're seeing that, so that's happening under the hood. So we were saying that case classes and tuples and H lists, you can convert between each other. So that they must be related, right? Well, in fact, in Scala, case classes and tuples automatically, by default, extend a trait called product. And that's not a surprise, because they're all product types, which is something that Clement was saying at the beginning of this morning, right? They're all product types. What is a product type? It's a tuple. Why is it called a product type? Because it comes, as Clement was saying this morning, from the idea of Cartesian product. So if you have a set A and a set B, the Cartesian A, Cartesian B, it's the set of all the pairs where A is an element of the set A and B is an element of set B. Confusing? That's not a problem. It's not important that you get it. It's okay if you know what a tuple is. It's enough if you know what a tuple is, because H-list, tuples, and case classes are basically the same concept. Is everything all right? Okay, cool. So, since now we have seen what the generic object was, we can understand a piece of the snippet of code from the Shapeless wiki. So, generic P, which actually here is called generic.aux, converts between product types and enables to use the T.toProduct syntax. So that's what's happening here. We are converting f into a function that takes an H list. All right, but what about the other thing, fn to product? Sorry, I switched the things. Sorry. What I was meant was this is gonna happen later. Actually, what we saw is that gen here is the thing that converts between a product type and an H list. What we're gonna see here is that this thing does the same thing for the functions. We just saw in the previous slide that in Scala we can convert a function with k-arity, so which takes k arguments, into a function that takes one argument, which is a tuple of size k, right? This is Scala built-in. And with Shapeless, we get another function, again with a very confusing name, toProduct, which converts the function f into a function that does not take a tuple, but an H list. Well, you know, they're the same, right? So this .toProduct syntax is a shorthand for this thing. So it's similar to generic. It converts a function into a function that takes an H list. So now back to the example. Sorry for confusing a bit things before, but we can understand all the stuff that's happening here. So first, we're getting a generic person instance, suppose that we are converting a person. So first we get the generic person instance, then we are converting f to the f that takes an H list, and then we're converting the person to an H list. And that H list, it's the same that is taken from the function. So now we can safely assume that the function can be applied to that H list. And so everything works. It compiles and it breaks otherwise. If we give to this function above something that does not match the signature of the function, or we give a function that does not match the product type, it will break at compile time. That's basically what we want. No boilerplate. No code generation, no reflection. And yet, there's something still confusing here. So what's aux? Okay, let's see this very quickly because it's not important for us today. It's just an implementation detail. So, um, basically, you saw that when we want to construct a generic instance, we pass it the type that we want to convert. So generic of person will give us an object that can convert between person and age lists. And you do not want to spell out the name of the type of the age list each time. So you would like to let Scala infer the things automatically. So that's what this .oaks does. It actually makes explicit this part. And why would you make that explicit? Well, when generic is used to enforce a constraint, then you might want to use the other form. And then what you're saying here is that generic PL is that generic P that converts P into an H list L. And then this Fn to product reads as that Fn to product F that converts F into a P to L. That's insert. F to L. Anyway, let's see this more clearly. So you're basically enforcing a constraint here. So what I'm saying here is that implicit values can be used to enforce compile time constraint. How does this work? Magic. It's magic. Or, like we like to call them in Scala, it's implicits. Implicits. Right? So, implicits are a controversial feature in Scala because they are hard to grasp for beginners and it causes age even to advanced users. And the term implicit may be arguable because it sounds like magic, you know? So let's delve a little bit into the details of this. Basically, you probably know what's the basic usage for implicit C. That is default values. Like you have a configuration object, you mark it as an implicit value, and then you can invoke functions without explicitly passing that object if it is in scope. Probably some of the stuff you're seeing now, it's a duplicate of what Pavel in the previous talk did. I hope this will give you another point of view and help you understand better the stuff. So what I'm saying here is that implicit values and implicit defs, in their most simplistic use case, are really a simple thing. You want to be able to invoke a function, but drop some of its parameters with defaults, like a default configuration object. The configuration, a fallback configuration for a database, I don't know. It might be a val, because it's a value that is fixed, a binding, something that will not change over time, or it can be a def. Who here followed the Coursera course on functional programming in Scala? Good, good. What's the difference between a def and a val? The val is evaluated by value, the def is evaluated by name, exactly. So each time that name occurs, then it's re-evaluated, so it can compute values. Now here I'm doing a bad thing because I'm using a side effect to generate a random number each time. This breaks referential transparency, but it's not a problem, it's just an example. So here I simulated a fallback configuration values that maybe it's fetched from some data source. So that's what are implicit values and implicit defs. If they are in scope, then I can invoke this function without giving it explicitly this value. Is everything all right? Okay, cool. So, but implicits can be used as logic predicates. And that's the turning point. I took the inspiration for this from a very interesting talk from a guy called George Leontiev. I hope I'm pronouncing this right. And it's entitled, "There's a Prologue in Your Scala." So, welcome to Prologue Italy 2016. It's our first meeting, so bear with me if I'll start from the very beginning. I hope here I'm pretty sure here there are pretty experienced Prolog programmers, so bear with me if I just give the very basics in order for you guys, all of you guys, to follow what's coming after. So, Prolog, it stands for Programmation Logique. It's French, right? It means, logic programming. It's a language for doing logic programming, but it's not so hard to understand. That's only four concepts there. Facts, rules to derive new facts, a knowledge base where these facts and rules live. And so what is a fact, for instance? A fact is a truth. It's something that we can assume as true. Like, today is sunny, right? It's true. You can watch at the window, have a look at the window, it's sunny. So a rule, it's a way to derive new facts, starting from facts that are already inside our knowledge base. So if it's sunny, I won't bring with me my umbrella. This is a rule. Then I can ask to some of you, do I have with me my umbrella? No, because it's sunny, right? Okay, that's really simple, okay? So what does executing a Prolog program means? It means solving the constraint in a query. And that's what your friend here, your colleague here just did right now. So it solved a query. You executed a Prolog program, congratulations. And a classic example, a syllogism. Every man is moral, Socrates is a man, then Socrates is moral. And you can encode this in logics using these fancy symbols. You're saying person of x, for all x's, person of x implies mortal of x. And then you can do a query. Socrates is a person, it implies that Socrates is mortal. Let's encode this in Prolog. A Prolog is not typed, so and you do not have to explicitly declare things before you can use them, so you can declare them when we use them. So you're actually saying a person of Socrates is actually defining the predicate person for Socrates. So we are saying that it is a fact that Socrates is a person. And we are asserting this inside the Prolog knowledge base. We're basically giving an evidence that this is true by providing the concrete fact. Then we can define a rule, and as you may notice, the rule is written in an inverted as compared to the logic. So in logic we will write mortal x implies person x. We just write it in reversed. So we say, I think it's reversed. Maybe it's reversed, right? No, it's sorry. They're inverted. So mortal of x, it's implied by person of x. So it's the other way around. And then I can query the Prolog interpreter, and it will say that it's true that Socrates is mortal because it knows that Socrates is a person, right? And I can also ask to give me all of the possible bindings for the variable x, variables are capitals, for which this statement holds true. So mortal of x is true when x is bound to Socrates. So the system is not only saying that the mortal of x is true, but it's saying that it's true when x is Socrates. It's given me an explicit, a concrete evidence, a witness that the fact may hold true, the fact actually hold true in our current knowledge base. Let's now see a little bit more complicated example. Mortal was just a unary predicate. This is a binary predicate. First I'm saying that John is a child of Carl and Carl is a child of Tom. Then I can define this rule that says for all a, b, and x, if a is a child of x and x is a child of b, then a is a grandchild of b. And it's written like that in Prolog. grandchild of A and B is true when there is some x such that it's a child of A and x is child of B. Right? Is it clear? Okay. And then we can test this. We can try to ask to the prolog interpreter, because it's interpreted, to give us all of the possible bindings for which grandchild holds. So grandchild x and y will say true, and x and y must be equal to John and Tom, because John is a grandchild of Tom. Let's get back. You see, John is a child of Car is a child of Tom, then John is grandchild of Tom. Right? So that's true. We can also try to find John's grandchildren by binding only one of the parameters, or finding Tom's grandparents. And then we can also try false predicates, like, is there someone in this knowledge base that is his own grandchild? Of course not. Not in this knowledge base. There's nobody that is a grandchild of Tom, and John has no grandparents. So thanks for coming to Prolog Italy. I hope we'll see you again next year, and welcome back to Scala-Italy 2016. And let me introduce a Scala dialect called Logic Scala, which is a superset of Scala which introduces two new keywords, fact and rule. And they work exactly the same as prologs. So first, let us declare relations and atoms, because in Scala, we have to declare them beforehand. So first we say, how would you do that? You can use types. And how would you define a type? Using a trait, for instance. So you can say that child A and B is a relation. And then you can define atoms, that is, those things that we used before, John, Carl, and Tom, using, again, traits. That's pretty basic Scala, right? Now we can introduce facts inside the knowledge base by providing to the logic Scala knowledge base, concrete evidence that the facts hold true. And what's a concrete evidence in Scala? Well, it's an object instance, right? So you can instance these traits with the facts. And in order to introduce them inside the Scala knowledge base, you have to prefix them using the fact keyword and give them a name. This is for backwards compatibility with Scala. So fact John Carl equal to a new instance of child where the type parameters are John and Carl, and the same for Carl and Tom. And now we can also write a rule. First we define the type grandchild A and B, which is the relation. Then we define the rule, which is the name. And in Scala, we have to define all the type parameters, all the variables that we're going to use inside the body of this rule. This is where the facts occur. This is the body of the rule. So at the same time, these rules must hold true. These predicates. So child A and X, child X and B. That's exactly like in prolog. And then, if both of these hold true, you can give to the system the new fact instance. And so you instantiate grandchild with A and B. Right? Please notice that if you drop all the redundant names, grandchild, XY, YZ, you basically get what you will write in logics. For all A, B, and X, child A and X and child X and B implies grandchild A and B, right? And then you can query the prolog interpreter, the logic interpreter inside logic Scala using this statement, query. You can ask if John is a grandchild of Tom, and it will compile because it's true. And you can also ask something that is false, and then the compilation will break because it's false. Plot twist. You see that coming, right? Logic Scala is actually Scala. Mind blown, right? Because if you just substitute fact with implicit val and rule with implicit def with rule, basically you're getting plain Scala, just Scala. And instead of a query, you will use implicitly, but it works exactly the same way. So, to recall the things a bit, implicit vals are facts in Prolog, implicit defs are rules in Prolog, type parameters in defs are the variables that occurs in a rule, and implicit parameter lists are the bodies of the rule. And so we can come back to our friend applied product and understand all of the stuff that's happening here. So what we are actually saying here, at the top you can see this translating into Prolog, and online you will find the whole translation of these type signatures, of these function signatures in Prolog. I'm saying that P must be a product, and that we have F and L, which must be an H list, and then we have R, which is the return type of the function. Then we pass a product type P and a function F, and here we're passing the tuple, and here we're passing a function which takes two integers. This was the strange signature we saw before. It's written in a more understandable way. What's happening here is that we're requiring these specific constraints. Given the product type P, we want to be able to convert P into an H list called L. And then we want to be able to convert the function we're giving called F into a function that returns R and takes that H list that we got from converting P into L. So that's why it compiles only when the signatures match. It's requiring these two constraints. And that's why it breaks otherwise. And now my last trick for today. Generic P and Fn to product are type classes. Because basically you can see type classes as predicates on types. If you have a value, if you have an implicit parameter, the value that you get is an evidence that the predicate holds, right? That's what we just saw in these slides. So when such an object provides methods, that's what we call a type class. And generic provides the method to and from. So that's a type class. And that is all.